Next, we're going to do some individual examples of computing antiderivatives, or families of antiderivatives. So computing the integral of various functions. Our first integral is the integral of sine of 3x dx. Now each of these examples will be just a tad spicier than the 5 basic antiderivatives that I showed you, in that the inside function won't be x by itself, but it'll be 3x or 3x plus 5 or something like that. But it won't be anything nonlinear, because when you get to a nonlinear inside function, that's when you have to be a little bit careful when you compute these antiderivatives or these integrals. And we'll learn techniques for doing that later on in our chapter on techniques of integration. For now, we'll just keep it simple, and the inside function will always be something of the form ax plus b. So the integral of sine of 3x. Now the integral of sine is negative cosine. So we're going to write minus cosine of 3x. Now normally we would multiply by the derivative of the inside. The derivative of the inside is just equal to 3. In this case, we divide by the derivative of the inside and we add c. Now this only works if the derivative of the inside is a constant. So the inside function has to be a linear function. It's the only time they'll get away with this trick, right? Now let's check our work. Well, what's the derivative of minus cosine of 3x divided by 3 plus some constant like this? Well, the derivative of the constant is 0, so I'm not worried about that. Okay, the derivative of cosine is minus sine, so we get minus negative sine of 3x. And 1 over 3 stays along. Then we multiply by the derivative of the inside, which is 3. The 3's cancel out, and we're just left with sine of 3x. So this is, in fact, the correct antiderivative. Our next example is to compute the integral of e to the 4x plus 7 dx. Well, if your intuition says let's start by rewriting it, you would be correct. We have e to the 4x plus 7. And then instead of multiplying by the derivative of the exponent, we divide by the derivative of the exponent. And it only works as long as the derivative of the exponent is constant. So e to the 4x plus 7 divided by the 4. And then we do the plus c. Right? So the reason is the derivative of e to the 4x plus 7 over 4, well, it's going to be e to the 4x plus 7 over 4. You start off by rewriting it. Then you multiply by the derivative of the exponent. So we multiply by 4. Those cancel out, and we just get e to the 4x plus 7. So the derivative of this really is this one right there. So it all checks out. Our next example is to compute the integral of the ln of 6x plus 2. Well, I take that back. Our next example is to compute the integral, one step ahead of myself, 1 divided by 6x plus 2. Well, this looks like it's 1 over x essentially, so let's try ln of 6x plus 2. So that's already off to a good start. And to correct for the fact that it's not 1 over x, it's 1 over 6x plus 2, we can think a little bit about what the derivative of this would be. The derivative of ln of 6x plus 2, well, we would write 1 over 6x plus 2, and then we would multiply by the derivative of the inside, which is 6. So when we take the derivative of this, we're going to end up with an extra 6 in the numerator. So to correct for that, we have to divide by 6. So we get 1 over 6 times the ln of 6x plus 2 plus c, right? And if you check the derivative of 1 over 6 ln 6x plus 2, well, we get 1 over 6. Now the derivative of ln of something is just the derivative of the inside, which is 6, and then divided by the inside. The 6's cancel, we just get 1 over 6x plus 2, so that checks out. And our final example is the integral of the square root of 3x plus 8 dx. Well, this is 3x plus 8 to the 1/2. So it would make sense that we would want 3x plus 8 Now we're adding 1 to the exponent instead of subtracting 1, so 1/2 becomes 3/2. Now, then we're going to divide by the new exponent instead of multiply, so we're going to divide by 3/2, which is like multiplying by 2/3. And then we're also going to divide by the derivative of the inside. So the derivative of the inside is a 3, just like that. So we basically get 2/9 times 3x plus 8 to the 3/2. To check, well, let's take the derivative of 2/9 times 3x plus 8 to the 3/2. The 3/2 comes down. Now when you do 3/2 times 2/9, we get, let's just do 3/2 times 2/9, and then times 3x plus 8 to the 1/2, and then don't forget to multiply by the 3 inside, so we get an extra factor of 3. Well, the 2's cancel. 3 times 3 over 9 is all 1, and we just get square root of 3x plus 8 because the 1/2 is the square root. So you see what we did. We started off by saying, okay, this is something to the 1/2. We added 1 to the exponent, so it's something to the 3/2, divided by the new exponent, so dividing by 3/2, we multiply by 2/3, and then divided by the derivative of the inside. Now we can only divide by the derivative of the inside if we get a constant. So we would have to get that 3 down there. Right, I'll show you an example where dividing by the derivative of the inside doesn't work. Suppose we have the integral of e to the x squared dx. Well, you'd want to rewrite it and then divide by the derivative of the inside, or the derivative of the exponent, which is 2x. Is that correct? No, it's not correct, because one way we can differentiate this, normally you would use the quotient rule, but in this particular case, I'd like to use the product rule, right? Because the quotient rule really comes from the product rule anyway, so let's look at it like this. So first of all, we get this function times the derivative of e to the x squared. The derivative of e to the x squared is e to the x squared times 2x, and then it's times the second function. But then we get plus this function times the derivative of this one. So then we get plus e to the x squared times the derivative of this. Now there's a 1/2 there, and then it's x to the minus 1/2. So the derivative becomes minus 1 over x squared. Now the first term here is on the right track. The 2x's cancel. But the second term throws everything off, right? So the derivative of e to the x squared divided by 2x is e to the x squared minus e to the x squared over 2x squared. So the reason it doesn't work is because when you divide by the derivative of the exponent, and the derivative of the exponent gives you an extra x here, it screws everything up, right? You can't just take the derivative of the top and ignore the bottom, because the bottom now depends on x as well. And so you have to use either the product rule or the quotient rule. They both give you the same answer in the end, which is this stuff. And you start off, one of the terms is exactly the correct term that you want, but then you get this extra term, meaning that this ratio here is not the derivative inside. And as I mentioned previously, e to the x squared doesn't have any simple antiderivative. There's no way in a finite number of terms to write the antiderivative of e to the x squared in terms of simple functions. So you might say, well, maybe there's something else I could do to fix this. There isn't. You're just kind of out of luck for e to the x squared. However, it's still a very important antiderivative to know, and there is an antiderivative out there that we will encounter in our studies in the future, but it's a new function, and it's literally defined based on the antiderivative. So in terms of the elementary functions you already know, forget about it if you're trying to write out the antiderivative of e to the x squared.